Hello everyone. So today we'll be talking about building a Raspberry Pi based Wheatstone bridge sensor interrogator. This is a video which is specifically made for third year BTech electrical engineering students at IIT Mandi, and this is part of their measurement and engineering course. This is some kind of a capstone project in the sense that whatever experiments they have been performing so far, they'll be bringing it together and they will be building a sensor interrogator which will be using the Raspberry Pi as a temperature logger. From this point onwards, I'll be directly referring to the students because this video is directly intended to them. So I hope this doesn't put you off. Alright, so let's get started. So let's look at the problem statement. So the problem statement can be something like this. Say a thermos manufacturer is approaching you and they would like to know how long they are able to keep hot water hot inside their thermos. So that is a kind of application we can keep in mind when working through this experiment. Apart from that, this can also be some scientific experiment where you'd like to monitor the temperature variations of some liquid, or you want to monitor the temperature of a boiler, whatever suits your purpose. This is a graphic rendering of what might appear to be a sensor connected to a thermos. Not ideal. This is generated by ChatGPT. As you can see, it has its own problems apart from the obvious bias that you can see here. And clearly we want the sensor to be inside the thermos, not outside. Regardless, just to give you a mental picture of what kind of problem we are looking at. Alright, what are the objectives? So we can actually break down the objectives into two parts. So the first part can be academic objectives, application objectives. So the application objectives can be to realize, say, a PT100 based temperature monitoring system. So the PT100 is a platinum resistive temperature detector. And the temperature resolution can be decided as per use case. So for instance, we are talking about two things. One, what is the temperature resolution itself, and the other one is what sampling rate you want to focus on. So both of these factors come into play, and these can be realized from use case to use case. And finally, this is an objective that we can think of, which is we want to record the temperatures using a Raspberry Pi because that will allow us to do some analysis on the measurements. And for the purposes of the course, we can say that we have some academic objectives. These are to use a Wheatstone bridge to transduce resistance changes to voltage, to use an instrumentation amplifier to amplify the voltages, and finally to perform suitable theoretical and simulation based analysis of the realized circuit, or for the matter of fact, using such theoretical and simulation based analysis for realizing the circuit itself. So these are the primary objectives, and the outline of the presentation which is going to follow is the following. We'll start off with a block diagram based system overview. Then we'll do a full circuit diagram, and we'll do a blockwise breakdown because the circuit diagram might look very intimidating at first. But if you look at it block by block, you'll realize that it's just a sequence of circuits. Just we have to pay attention to what feeds into what. That's basically it. Then we'll talk about implementation because you'll have to build the circuit in the lab, and it is always helpful if you can do things systematically. While you can always realize the full circuit and see whether it works, perhaps it's not the best way forward if you haven't done this before already. So going systematically through each block and analyzing each block and making sure each of them works will ensure a greater success towards the end of the day. Right. I also lay out some task completion criteria. Sorry, it should read completion, not competition. So there is no competition here. We are all learning here. So it's task completion criteria, and the completion criteria are laid out so that we can grade you. Right. And I'll also show you a video of the circuit in operation. So I spent a day and a half putting the circuit together, making sure that the circuit as it stands works. You wouldn't face any engineering problems. So mostly you'll be facing some academic questions that you'd have to handle. Right. Okay. So let's get started. So the full circuit, if we look at the full circuit, let's start with the block diagram. So the block diagram is simply something like this. You have a Wheatstone bridge, you have an instrumentation amplifier, and you have an ADC which connects to the Raspberry Pi. Now this is the bare bones essential, but now when you want to engineer this interrogator, there are a couple more things to be taken into account. For one, you'd have to supply voltage to the Wheatstone bridge, and what we are trying to do is we are going to use only one source of voltage. So this source of voltage is going to be plus minus 9 volt. For the moment, we are going to use the power supply that we have in the labs for this. But eventually it would be worthwhile to investigate whether this plus minus 9 volt power supply can be replaced with, say, batteries or say a power bank. So this is something we can think about later. The instrumentation amplifier also needs some biasing, and we'll see why in a moment. And finally, the MCP3008 will also need a supply of the reference voltage. And all of this is going to come from a single supply voltage, right? So now the question is, how do we build the circuit in this case? Okay. So if we look at the full circuit, it's going to look something like this. So there are too many things happening at the same time. I'm sure you can recognize the Wheatstone bridge here. You can recognize the instrumentation amplifier and the MCP3008. And there are a few other unknown players at the moment, and we'll walk through them step by step. Yep. So let's start off with the voltage divider with buffer amplifier. So this is the circuit which is going to supply the voltage to the Wheatstone bridge. So you'll see that there is a voltage divider, and we also have an op amp. So what goes? So the input voltage is the source supply, which is the VCC. So what we are going to do is we are going to use the voltage divider to drop the voltage to suit the inputs accordingly, which is what we need to do anyway. And the buffer amplifier is required for avoiding loading effects. So you would see, if you build the circuit without the buffer amplifier, you will see that there are problems, and you will see that the output of the Wheatstone bridge no longer follows your theoretical expectations. So that's primarily because you have loading effects, and to avoid that loading effect, you use this buffer amplifier. And the resistances which are indicated here are chosen to give an output voltage of roughly 5 volts. It's 5.35 something. It's roughly 5 volts for a VCC of 9 volts. So that's the reason why we have this here. Then we come to the Wheatstone bridge. Now in the Wheatstone bridge, you'll see all the arms are chosen to be equal to the PT100 rest temperature, which is at 25 degrees Celsius. It's roughly 100 ohms. In place of the unknown PT100 resistor, what we do is we place a trim pot, and this trim pot is being used for calibration. And this Wheatstone bridge is driven by supply from the buffer amplifier of the previous stage, right? Okay. Advancing to the next stage, we have the instrumentation amplifier. Now, as I said previously, RG can be chosen to match the application, but yeah, there's a small caveat. We'll talk about it later. The output voltage is shifted by an application of voltage to Vref, and this is actually required because at the end of the day, the instrumentation amplifier is a differential amplifier. The Wheatstone bridge is also going to give you negative voltages. The instrumentation amplifier will also give you negative voltages. You cannot input a negative voltage to an ADC. And because of that, what you do is you apply an offset, and that offset is realized using this buffer amplifier configuration. The trim pot is used to drop VCC to the appropriate voltage level. So it's like a volume control, if you may think of it as so. So it's like a volume control, and that is going to adjust the bias level. Then we come to the MCP3008 and the Raspberry Pi. The connections of the MCP3008 is actually available on the GPIO0 read the docs page. You can also follow the same circuit, and it's just a one-line code to read the voltage values from the MCP3008. The important thing here is, again, we are using a VCC of 9 volts, so plus minus 9 volts, and we want to drop it to 5 volts. The maximum voltage that you can apply to the MCP3008, the source is 7 volts, so 5.35 shouldn't be a problem. Similarly, we can also apply the same voltage to the Vref input of the MCP3008 for the scaling wire, right? Okay, So this is the overall circuit, and I now hope that it's a bit more familiar. So we have the source stage, we have the Wheatstone bridge, we have the amplification stage, and finally we have the MCP3008. Ideally, you want to put a low pass filter here to avoid aliasing effects, but given that we are going to perform very low frequency measurements, what we can do is we can always average out whatever readings we are getting here at the MCP3008, and that should serve our purpose for now. Otherwise, you can simply put a passive or an active low pass filter here to suit the bandwidth of the ADC. Okay. Now let's look at the implementation. So this is an actual photograph of a working circuit, and you can see it's all spaghetti wires all over the place. So this is okay. It doesn't have to be pretty for now. It has to work, and that's more important. What I would say is, instead of using the standard jumper wires you would use typically for breadboard connections, you can try using bare wires, breadboard wires, to make these connections, as then they'll be much more cleaner and much more easier to debug at a later stage, right? So let's look at it in a bit more detail. So again, we have the Wheatstone source. So you have the input bridge here that is followed by the buffer amplifier, and then that buffer amplifier is connected to the Wheatstone bridge. So it's no longer the diagonal that you're commonly familiar with. So it's kind of broken down in this fashion. Then you have the trim pot, which can be replaced with the PT100 sensor once you are done calibrating this interrogator. You have got the instrumentation amplifier here. I think I put in 10 kilo ohms if I'm not mistaken. So a 10 kilo ohm resistor here. There is the amplifier bias stage here, which feeds into the VREF, as you can see here. And then that is followed by the MCP3008. So you can see the output is getting fed into the first channel of the MCP3008, and here you have the wires which is connecting to the Raspberry Pi. So it's going to the Raspberry Pi, and you can also see it on the desk here. So you can see the wires running into the Raspberry Pi, and the Raspberry Pi interrogating the voltages, while I'm simultaneously also observing the analog voltage which is coming from the instrumentation amplifier here. All right. Okay. Now there are some general recommendations, and you can think of this as good practices to follow. So check all the wires for continuity, especially if you are using your breadboard banana patch cables. Sometimes these wires lose connectivity over a period of time. That's why it's best if you just use these breadboard wires directly from the spool and connect them. So at least you'll be assured of the continuity. Make sure that the components are firmly connected to the breadboard. So the breadboard is more for prototyping, and it is not designed to be durable. So what this means is, if you happen to kind of flip it over, or say just falls off the table, there is no guarantee that the components are properly connected to it anymore. In fact, when I was making the circuit, when I was touching one of the resistors, I saw that was a bit loose. I had to trim it again and again put it back into the breadboard to make sure that I got appropriate connections. So make sure the components are firmly connected to the breadboard. Go blockwise. So it is quite tempting to kind of build everything at one go, or kind of dividing the blocks amongst yourselves. What I would say is, make sure that all of you work on one block at a given point in time. When I say all of you, I mean, of course, within a team. So all three or all four of you work on a given block at a given point in time, and divide the tasks such that you're able to analyze it rapidly, each block at a time, right? And this means that you're not only testing the components, you're also testing the components and the blocks. So we'll see what I mean in the upcoming slides. This will ensure that each block is working as a unit, so that when you line them up and connect them together, it will be easier to debug once you figure out things are not working, or they're not going according to what you're expecting, right? And to this end, you have to use multiple devices. So you have to use your multimeter, you have to use your signal generator, your power supply, your oscilloscope, and of course the Raspberry Pi, which is reading out the voltage levels, right? So make sure that you are using them interchangeably, so you can also cross-validate across measurements. And finally, keep notes of observations from each step. This could be in terms of the resistances that you have used. Maybe you're not following the same circuit which are given. You feel that, okay, this can be done slightly better. So you note that down. You note down the values which are coming out from each stage. This is all important because given so many wires and so many components, believe me, even this number of components is quite a lot because there are several factors to be considered. It helps if you keep a record of things as you go along. Right? Okay, so now how do we handle each block by block, right? So let's start off with the voltage divider, and what I would recommend is first you test the output voltage from the voltage divider alone, just to make sure that you're getting the 5.35, and this way you can be assured that the resistances and the connections are proper. This is the first and the most important stage. If this stage is not supplying the voltage properly, everything else fails down the line, right? Then what I would say is you connect the op amp in the buffer amplifier configuration, check for the offset level. So this is when you are not actually connecting the buffer amplifier to the output from the voltage divider. This is just the operational amplifier. You are making sure there is no offset from the LM741, and you can check this by connecting both the inverting and the non-inverting inputs to the ground. And if there is an offset, either you can replace the LM741s, because typically off-the-shelf LM741s are fairly offset nulled, but if they aren't, then you might want to use an additional pot to correct for the null, right? And once you have done that null correction or null check, then what you can do is you can connect the output from the voltage divider to the op amp, right? So this way now you can be ensured that the output voltage is actually the right output voltage you want it to be, which is around 5 volts, 5.35 volts. Okay. Now we have the Wheatstone bridge. You will notice that there is an additional R3 resistor here. So this is something I would like you to think about why I have put it here. But for now, what you need to do is you start out by checking the trim pot resistance values. So make sure that the trim pot is working properly as you turn it. So you can use a multimeter for this stage. Then you run the simulation considering the inclusion of the 2.2 kilo ohm resistor. So this is because if you know that for a 5.3 volt source which is applied to the Wheatstone bridge, you're going to get this range, you should also see whether in experiment you're getting the same range. Maybe it's not working out properly, then you need to debug your circuit. So having a simulation of the output characteristics always helps. And make the connections on the breadboard, ensuring all the resistors and the trim pots are well connected. And this is again very crucial because this is the stage which is going to read out the sensor values, and you want this to be as robust as possible. You don't want things to be moving around even when you're adjusting them. So you want to be sure that if you say press down on one of the P or the Q or the R or even the trim pot, the output voltage VBD should not change. So that basically means that your circuit is quite robust, right? You verify the output voltage on the Wheatstone bridge as you vary the trim pot. Now, when you have a trim pot, it's not very easy to measure the resistance value while you are changing VBD. So you can do some ballpark analysis to make sure that you're getting approximately the correct values. So you can try that, or you can replace the trim pot with fixed resistors to make sure that the Wheatstone bridge is working properly, and then replace it with the trim pot. Take your call. That's not a problem. Okay. Now, if you want to test the instrumentation amplifier, we have already done this before. So this is very standard way of doing this. So first of all, you want to test the buffer amplifier connection and verify the output voltage variation with the trim pot setting. So we know how to work with the trim pot. We know how to build an LM741 based buffer amplifier now. So this can be built separately, and you can verify whether you're getting the right outputs. Once you have verified that, you can again verify the working of the instrumentation amplifier separately. Again, we have tested this. We know how to do this. We can supply 2 different sine waves here of different frequencies and check whether the output matches your expectations. So we have done that. Or you can choose any other way of verifying whether the instrumentation amplifier works. Then you can connect the bias to the amplifier and adjust it so that the amplifier output is positive for a full scale excursion of the bridge. So this is an important bit. This bit is important because you need to know what is the full scale excursion of the bridge. So you expect, say, the temperature to vary from 0 to 150 degrees Celsius. Or in the case of the thermos, you know that the temperature is not going to go beyond, say, 100 degrees. Still, as a safety measure, you keep a full scale deviation of, say, 0 to 100 degrees Celsius, right? 0 to, say, 120. So if you know that your input resistance is going to change in this range, then corresponding to that, you can find out what is the VBD output from the Wheatstone bridge, the voltage output from the Wheatstone bridge, and then accordingly you can adjust the gain such that the output voltage does not exceed the expected value of 5 volts. And also you can make sure that, because now you know that the temperature is going to change from 0 to 100 degrees Celsius, you also know what is the maximum negative voltage that you can expect, and accordingly you can adjust the bias using the trim pot in such a way that you never get negative voltages at the output of the instrumentation amplifier. Now you want to choose the gain such that the output from the amplifier is limited to 5 volts, and that's because you are going to supply a 5 volts to your MCP3008 as the reference voltage. So you don't want the input voltage to the ADC to be greater than 5 volts. And that is why you have to choose your RG value appropriately. And this is what I mean by choosing the RG value on a case-by-case basis. So depending on your application, you can change the value of RG. Depending on your circuit configuration, you can change the value of RG. So this is more of an engineer's or an instrumentation engineer's choice. And also, of course, if you want better resolution, you might want to increase RG more. So that's the engineer's choice. Right. Now the MCP3008 and the Raspberry Pi. So first of all, you have to test the voltage divider configuration as before. So you make sure that you are getting less than 7 volts, because that's the maximum voltage you can apply to the MCP3008. And if you're getting a 5.35, you can apply this both to the VCC and the VREF of the MCP3008. And to test whether the MCP3008 works properly, you can use a trim pot. So we have done this in the last lab. So we basically use again another voltage divider, which is going from a range of 0 to 5 volts. You use a potentiometer and you apply a voltage input of 5 volts, and then you can turn the trim pot so that it goes all the way from 0 to 5 volts of voltage drop, and that can be measured using the MCP3008, right? And you can check whether the Raspberry Pi is reading these values as you vary the trim pot settings. So if you are at a minimum, it should read close to 0. If you are at a maximum, it should read close to 1023 or 5 volts if you are doing the scaling already, right? So this is, you check again. So each block has to be tested, validated, vetted, make sure that they are all robust, and then finally you can bring all of them together. Now when you are bringing all of them together, the characteristic of interest is the output digitized readout of the Raspberry Pi with the trim pot. So what you are doing is, once you know that every part of the block is working, ideally if you connect everything together, everything should start to work. And when it starts to work, you can vary the trim pot from its minimum to its maximum, and then accordingly you can see what is the readout on the RPi, and you can have a transfer function between the resistance and the RPi. Now there are two things you could choose to do. One is you can either replace the TP 100 ohms with some fixed resistances so that you have a readout corresponding to some fixed resistances. Alternatively, you can also use a digital potentiometer here, and by scanning the digital potentiometer, you can then do an automated calibration of the whole interrogator circuit. So this is slightly advanced because there'll be too many moving blocks here, and that's why I did not include it. I would recommend inserting fixed resistances for now, and you can also keep the trim pot for quick debugging. Now an oscilloscope or multimeter can be used for measuring voltages, resistances of interest for calibration. Again, good practice is, if you see that things are not working properly, you can use your oscilloscope as a probe at different points along the circuit, and when you're using it as a probe, you can check whether you're getting the right input and output voltages or whether you have the right resistances in place. You have to be careful that when you're measuring resistances, the circuit should not be active. If the circuit is active, then it won't give you a right reading. So we have seen this before. And finally, this is the important thing that you need to do, which is you have to derive a scale factor. So the scale factor here is, because the Raspberry Pi is going to give you it is going to give you a digitized output. So it's going to go from 0 to 1023. That has to be converted to either an appropriate resistance value or an appropriate output voltage that you're getting from the INA126. Ideally, it's the resistance value. If you can do that, then that's the best case scenario. So you have to find a scaling factor between the bit levels and the resistance value. So that can be done fairly easily. But this is again something that you'll be evaluated on what approach you take, what strategy you take, how do you choose a strategy that minimizes the errors of scaling. So that is the task that I set before you, right? Okay. And here's a task implementation criteria. The task implementation criteria is the following. So you have the verification of the output voltage from the voltage divider and buffer, numerical simulation of the Wheatstone bridge output. So this is something that I would really like to see because you have done this and this is very useful. Experimental verification of the output voltage of the bridge for different values of the trim pot or fixed resistances. Demonstration of the instrumentation amplifier and bias offset. Then experimental verification of the output from the instrumentation amplifier for different trim pot settings. Demonstration of the MCP3008 working. And then finally, experimental verification of the digitized output from the MCP3008 as a function of the trim pot setting. So you can see the task completion criteria, while they are not in order, it kind of gives you an idea how we are actually working through the different blocks of the circuit. And at the same time, we are also bringing them together one by one. So first we are, for instance, we are checking the instrumentation amplifier and the bias, and then we are combining the instrumentation amplifier with the Wheatstone bridge to see what are the different values for the different trim pot settings. Then again, we are checking the MCP3008 separately, and then we are bringing everything together. So there's a systematic way of doing things, and this way you can be sure that your circuit will not fail. Hopefully. And finally, you have the systematic determination of the scaling factor, converting digitized MCP3008 readout to voltage, and its experimental validation. So we'll also have the TAs walk around with an unknown resistance. So we'll put in an unknown resistance in your bridge configuration, and we will see whether the system that you have developed is able to read out that value directly, right? So yeah, and the proof of the pudding is in the eating. So I'll show you a quick video of the configuration as it works. Okay, so you are looking at a full interrogator circuit, and in this full interrogator circuit you have, first of all, you have the supply voltage connection, then you have a buffer amplifier followed by the Wheatstone bridge configuration, then you have the instrumentation amplifier, then you have the offset bias for the instrumentation amplifier, and finally you have the MCP3008. So this is being driven by a 9 volt power supply plus minus, and what you are seeing here is the oscilloscope output from the instrumentation amplifier. So currently it is reading a value of around 600 millivolts, and simultaneously I'm taking a readout from the MCP3008, and that is giving me a readout of 0.59 millivolts, which is fairly close. And as you will see in real time, when I adjust the potentiometer, the readings will also change. So you can see here there are some minor disturbances because of loose contacts on the breadboard, and these can be improved. So we let it settle for a bit, and now you can see that the output is 947, and here it is reading out somewhere around 935. There's a slight error, and that's probably because of the calibration value, but that can be adjusted. But this is basically the configuration that you'll be looking into on Monday and the week following.